All right, so we did regular probabilities last time. Many of you still need to watch the video. Today we're going to talk about conditional probabilities, which I did introduce in the video last time, and find expected value. Expected value is basically the average. So recall that events are independent if the probability of A and B happening is the same as the probability of A times the probability of B. That is the definition that you need on your paper. And I talk about this in the video from last time, and I'm going to go over it again. Normally, on a normal year, I have sticks and a little can. And I'm one of those mean teachers that pulls out a stick and calls your name, okay? And in this case, I'm showing that I have 10 boys in my class and 20 females, okay? If I asked you what is the probability of me reaching in and getting a guy, would you guys be good that it's 10 out of 30? Okay, I put the guy back, so I reach in and get another guy. What's the chance of that? 10 out of 30. If I have a guy's stick, put it back and say grab another guy, still 10 out of 30. These two events are independent, okay? Getting a guy on the first time did not affect my chance of getting a guy on the second time because I put it back, okay? They don't relate. So if I wanted to find the problem of getting a guy and getting a guy, okay, probability of M1, M2, and we often do a little and here. We talked about this last class. Okay, that means and. It's just the first one times the second one. And whatever that gave me, okay, would be my answer. That is independent, the fact that we could just multiply them. Instead, however, if I had put one back, and I think I have it under here, but I'm just going to talk about it real quick. If instead I get a guy and I don't put it back, the chance of getting a guy is 10 out of 30. Leo, check the printer for notes. And then if I don't put it back, what's the chance of getting guy number 2? Just in general, if I don't put it back, what's the chance of getting another guy? What out of what? 9 over what? But there's only 29. Yeah. 9 over, and it was just that I couldn't hear you. 9 over 29. There are only 9 guys left in there, and there are only 29 sticks. Because I didn't put it back, this one was dependent on this one, right? So that's dependence, and so the formula changes. I have it written down right here, I'm pretty sure. Okay, that the first guy would still be 10 out of 30. Okay, but the second guy, given that the first guy happened, that's actually how you write it, would be 9 out of 29. Okay, so if I don't put it back, it's the first one times the probability of the second one that's changed given you got the first one. So you still multiply them together, but we have to know what you got on the first time in order to change that second probability. So this little highlight part right here, that's the difference in the two formulas. So to say that again, those are the two formulas that you use when you're going to multiply or when you need to find out two things happening at the same time. But it changes if they're not independent. So now we have a given formula. How do you find the probability of B given A? B given A. Okay, given that A already happened. Well, that's the finding the both things all over the probability that A happened, which can be written like this. And we're going to do some examples of those. Okay? So, probability of B given A means the probability of B occurring assuming A already occurred, which is what we found right here okay? Probability of getting a second guy, given the first one already happened, is the probability of both things happening all over the probability of A happening. And this formula, this example, we didn't have to use the formula because we just thought it through. So I'll give you some examples of the formula right now. Okay, so using the formula, observe that A and B is equal to B and A. It just means both things happen. Doesn't matter which one you put first. Okay? But A given B is not the same as B given A, necessarily. So for example, if we went up to the sticks, if I said, what's the probability of getting a male given you got a female? Okay, well, getting a female, you now only have 29 sticks in there, right? But how many male sticks are still in there? 10. However, probability of female given male, if you already got a male, there are 29 sticks in there, but how many female sticks are in there? So notice that these do not mean the same thing. You guys good with that? Okay. So here is the typical formula. The top part right here, the order doesn't matter, okay? But we usually, if we put A first, we put A first. And if we put B first, we put B first. What does matter is the given part is what's down here. Okay. It says, find the probability of drawing 2 queens. And we're doing it independently because I'm going to replace them. So queen and a queen. Okay. Well, now again, we're just finding different probabilities. That'd be the probability of getting a queen, putting one back, and getting another queen. So probability of queen 1 times the probability of queen 2. Notice this probability stayed the same as this one because they were independent. We put one back. You have to show work like this, especially if we get a paper final. I don't think we're going to, but they give credit like that. Like sometimes they give credit for this number and credit for this number. So even if you didn't know what was going on the top, you could get 50%. That's a 2704, I think. Okay, now let's do it dependently. So probability of getting a queen and another queen, okay? Well, the first one is 4 out of 52, but I've already gotten a queen. And there's only 4 queens in there. So the next one is 3 out of 51. So this just is showing dependent versus independent. Okay. Notice it's the probability of queen 1 times the probability of getting queen 2, given I already got queen 1. That makes it the dependent formula. I mean, this one's still that dependent formula, given I already got queen 2, but getting queen 1, we didn't need this because it didn't change anything. All right, so the next thing we have is a tree diagram. I always fight with this. I much prefer the tree diagram. They prefer the little chart. We're going to do both. Okay, so we're going to read this little story and then we'll draw the diagram. A virus infects one, it should say one in every 400 people. This is like sadly appropriate. Okay, a test used to determine the virus is positive 90% of the time. If the person has the virus, and positive 10% of the time if the person does not have a virus. So that is a false positive, okay? So find the probability of A given B where A is you have the virus, A complement is you don't have the virus. Now, I probably would have called these V and V complement because it makes more sense to me, or positive and negative instead of B and B complement. And you're welcome to do that. You don't have to give them arbitrary letters. If I was doing this on my own, this would have been V for virus and P for positive. Okay, any questions with what this notation is? Okay, so here's how you do the tree. You try to think of all the different ways to do it. So don't worry about the highlights yet. This is what you're drawing. You okay? Draw a little V right here. A for virus and A complement is no virus. The chance of having a virus is 1 out of 400, which means the chance of not having the virus is 399 out of 400. So that's the first thing you figure out. Do they have the virus or not? Now, if you have the virus, the chance of getting a positive test, we're calling that B, but you can just put a plus if you want, is 90%. So 90% chance that test will be accurate. And there's a 10% chance that test will give you a negative, so be inaccurate. That would be a false negative. Again, you could, if you had done this, just use the B and V, or the positive and the V, or you could use A and B. You didn't have to use both. Okay, so then that's the given part. Given you don't have the virus, the chance of getting a positive test, that would be a false positive, is 10%. The fact that these numbers are the same but switched is just a coincidence. Doesn't always work that way. Okay. And the chance of getting a correct negative, right, no virus, is 90%. Okay, that would be a negative if you don't have the virus. Now, you could just answer these questions. So I'm going to show you this little chart, but you can decide to write it down or not. If I wanted the different combinations, okay, this combination would be right here, A and B. The probability of virus and getting a positive. Remember, and is multiply, so we do this times this. This is already a dependent one. This 0.9 is the probability of positive given you have the virus. It's already figured out for you. Okay, that would be the blue path. The orange path, which is this one, A and then B, so that's getting a false negative, would just be multiplying the two together. Again, you can choose to write that down or not. I just usually make the chart and then do the work. I don't do all the steps. The green path here, you don't have the virus, but you got a positive, would be multiplying those two together. And then the red path, you don't have the virus, but you got a negative. So again, the correct response would be that. So you have these three probabilities. I don't usually, like I said, figure those out in advance. It's not necessary. I just make a tree. Okay. Now we want the probability of A given B. A is you have the virus given you got a positive test. Right? There's a chance you don't. Now we know you're more likely to get a false negative than a false positive if you're talking COVID. But in this case, you're going to use the formula. That's the probability of A and B. So that's the blue one, right? This and this. All over the probability of just B, because we only care about the people that got positive tests. That's what we know happened, is that you got a positive test. So the probability of positive test would be this one over the green one. And usually I just figure out the work in the fraction. But that's how you use the formula. A and B go down both parts. All over B. How do you get to B? There's two ways to get to B. So both of those have to be on the bottom. You can get to B blue, or, told you or means and, or means plus, or you can get to B using green. And then you put that in your calculator and you'd get 2.21% chance of having the virus given you got a positive test. What? That doesn't seem right. Oh well, okay. Here's another way to do this. We're gonna make a table. Are you guys ready for me to scroll up? Okay, I want you to copy down a table that looks like this, a 3 by 3. All right, so here's another way to do it, is to make a table. Because if you have a table, you don't actually have to use the tree or use the formula. So it says first thing, okay, notice that this is going to be those that have the virus, those that don't, positive test, negative test, okay? So first thing you do is let n be some number. Pick a number big enough that if you times it by the probabilities, you don't have a decimal. So you could times it by 100, times it by 200, but I want to times it by the probabilities and not have a decimal. If you don't mind decimals, that's fine. You could always just let n be 100 or 1,000. Okay, so it's an arbitrary number. So step 2, find the probability for how many people have the virus. Well, we said 1 in 400 have the virus. So if we're saying we're going to test 4,000 people, 4,000 times 1 in 400, that means 10 people have the virus out of 4,000. That's why I picked 4,000, because the original probability was 1 in 400. Could you pick 1,000 or something? Sure, and you'd have decimals and just run with it. Okay, now we want to know how many people don't have the virus. Well, if we tested 4,000 people and 10 of them have the virus, 3,990 don't. I think these tables are a pain to make. So for me, if I'm given a table, I celebrate and I use it. If I'm not given a table, I use a tree. I don't care what you do. Okay, for number 4. Now we want to know, 4 would be this box right here. We want to know how many people are positive and have the virus. Okay, well, we had a probability for that. We said, if you were positive, the chance that you had if you had the virus, the chance that you were positive was 90%. They gave that to us up here. Okay, so 90% of those that are positive, of those that have the virus is 9. We know that 10 people have the virus and 90% of those will get a positive test, right? Which means for the next step, one of those people would not. They would be a negative test. So we've dealt with all the people that have the virus. And we know there's 4,000 people total. Next, let's look at the people that got a positive, but they don't have a virus. Okay, so, well, I know 10% of people without the virus get a positive. Since 3,990 don't have the virus, 10% of that is 399. Well, okay, 3,990 minus that 399 is 3,591. Those are the negatives that don't have the virus. And you can fill in the table. Once you have one of these tables, getting the answer is super easy. They're supposed to be, excuse me, this should say 408, right? 9 plus 399. Okay, so it says, what's the probability of A given B? What's the probability of A having the virus given you got a positive test. Well, how many people got a positive test? 408, right? Because this is the positive test row. Of that positive test row, how many have the virus? 9. So once you have the chart, it's super easy to get your answer. And 9 divided by 408 is the same answer from up here. So it just depends on if you want to have to make a chart or not. Any questions? Okay. Pause for just a second. So we're going to talk about random variables. Okay, a random variable is a numerical variable whose value depends on the outcome of a chance experiment. For example, flipping the heads in number of heads in 3 coin flips, right? That's chance, random. Okay, and we're actually finding a number of heads in 3 coin flips. Or I randomly grab one of your pencils and measure it, the length of a pencil. D is for discrete, okay? 3 coin flips is a discrete number, because you could have 0, 1, 2, or 3. And continuous would be a length of a pencil. It'd be a continuous variable. A random variable is discrete if it's a set of possible values in a collection is a set of isolated points. So again, we could have 1 head, 2 heads, 3 heads, or 0 heads. Notice that it's just isolated points on the number line, so it's discrete. A random variable is continuous if its set of possible values includes an entire interval on the number line, right? I could grab your pencils and they'd probably be between 1/2 inch and 12 inches long. I guess one of those novelty long pencils, right? Some other examples would be randomly grabbing people's feet and asking what's your shoe size versus foot length, okay? Or age versus number of birthdays. Number of birthdays, you're 17, you're 18. But age, you're 18 years old, 2 months, 3 days, 4 hours, 6 minutes, 2 seconds, 4 nanoseconds, right? So that's the difference. So we're going to have what's called a probability distribution. It's a list of all possible outcomes of a random variable. And in this case, we're talking about discrete. Okay? And in this case, we're going to say that our random variable is the number of heads in 2 flips of a coin. So it's discrete. And we'd have something called a sample space. A sample space is the set of all possible outcomes, which is on the video from last time, right? You could get 2 heads, a head and then a tail and then a head, or 2 tails. And if you wanted to think about the separate probabilities, the probability that x equals 2, i.e. there are 2 heads, is 1 out of 4. 1 out of these 1, 2, 3, 4 outcomes, so it's 1 out of 4, okay? The probability of getting a head and then a tail, or a tail and then a head, is 1/2 of getting 1 head, okay? Well, there's 2 ways that could happen out of the 4 possible ways, so that's how we get a half. And lastly, the probability of getting no heads, that's 1/4. Notice that these have to add up to 1. To be a complete probability distribution, a valid probability distribution, they have to add up to 1. You could have also found these values using the multiplication rule, right? The multiplication rule would have said probability of 2 heads, well, chance of getting 1 head is 1/2, times the chance of getting another head is 1/2, which is how we get 1/4. Okay? For this other one, we could have said, okay, chance of getting a head is 1/2, chance of getting a tail is 1/2, or we get a tail and then a head, 1/4 plus 1/4 is 2/4. So you can use common sense or you can use the algebra. So another way to display this then would be called a probability histogram. You don't need to draw the curve. Notice that there are spaces in between. It's because it's discrete. I totally could have done this. 0, 1, okay, 1 to 2, 2 to something like this. This would be, actually, it would change it a little bit. This would have been 0, this would be 1, 2, and 3, and it would look like this. I could have made it continuous. This would be 0 up to, but not including 1, so this would be 0. These would be the 1s, these would be the 2s, okay? But I made it a discrete one, so I left it discrete. And notice this side is a probability from 0 to 1. Notice my labels. Probability here, number of heads here. It does look normal, but we don't know if it's normal, okay? I said binder check today. There's not enough here of you in here to do that. We'll have to probably do it right after Christmas. I am doing a binder check before the end of the year or end of the semester. All right, so the probabilities in a distribution give information about the long run behavior of the variable. That is, the probabilities are relative frequencies. For example, if x equals 2 is 25, then after many observations of x, many observations of you flipping a coin twice, you will get 2 heads 25% of the time on average. Okay, it's not that you're guaranteed to get 2 heads 25% of the time if you just do it a couple times. All right, so now we're going to talk about the mean value, which is also the expected value. Okay, and it describes where the distribution is centered. Hopefully it's symmetric, which would make it centered. So let x equal the number of license plates on a randomly selected car. Okay, the probability distribution of x is shown in a table below. How do I know it's a probability distribution? Because they all add up to 1. Because it has to be every possible outcome to be the full distribution. What this is saying is if I randomly pick a car, there's a 5% chance it won't have a license plate. There's a 25% chance it'll just have 1 license plate, and a 70% chance it'll have 2. Okay? I want to know the average. Here's the formula to find the average. It says take every variable, times it by the chance of it happening, and add it up. So that's what I did. 0 license plates times the chance of that happening, plus 1 license plate times the chance of that happening, plus 2 license plates times the chance of that happening, and I get an average of 1.65 plates. If you wanted to find this in the calculator, okay, you need to know how to show work, but you could just put the variables in list 1. Now you could have also done this on your original homework when it had the list of variables and the frequency that they happened, okay? Variables in list 1 and the frequency. If you're falling asleep, go get a drink real quick or stand up on list 2. Okay, and then you do stat, calculate, 1 variable stats. Again, only one thing is varying, the number of license plates, okay? But my frequency, how often it's supposed to happen, well, that's the probability that it happens, goes right here. Calculate. There's my average number. Oh, I must have had the numbers in wrong. Let's see. 0, 1, 2, 0, 5, 0.7. There we go, 1.65. Notice my standard deviation, there's no sample because it's not a sample. It could tell it was talking about everything, is 0.572. So I'm showing you the formulas and you need to understand them, but you can use your calculator. Okay, So that is the average or expected value. They are synonymous. I want to show you where it's derived. You don't necessarily need to know this, just follow along. Let's pretend we had 100 cars. If we had 100 cars, right, wouldn't that mean that 5 out of 100 of them would have license plates if it was perfect? Because it's 5%. And 25 out of 100 would have 1 license plate. I should have said 0 license plates. And 70 out of the 100 would have 2. That's a theoretical perfect population of 100 cars, right? So thinking you're going to have 5 out of 100 have this. We just use the formula. That's every value times the chance of it happening plus the next value times the chance of it happening. If we simplified the math and made all the numerators together and all the denominators together, guys, it's just your regular old average formula. Isn't the average add them all up and divide by the total? Well, we would have 5 plates with 0 license plates, so 0 plus 0 plus 0 plus 0 plus 0 plus 25 plates with 1 plus 1 plus 1 plus whatever, plus 70 plates with 2 plus 2 plus 2 70 times, divided by the total. So what I'm showing you is this formula right here is just your total, your normal average formula. Add them up and divide by the total. Okay? All right. Now, suppose I asked you to play a betting game with me. You bet $5, and if you draw an ace of hearts, I will pay you $100. If you get any other ace, I will pay you 10. And if you get any other heart, I will give you your money back. Here's the deal. You're making a table to figure out the probabilities for each situation. You have to be careful because it says create a probability for the amount you win. Well, are they wanting that the total amount you won or the net amount, right? If you took $5, if it cost you $5 to play the game, then really if you win the first time, your win is $95. So do they want the take-home amount or do they want that you won $100? You have to be really careful and look at the question because you could argue both. In this case, it says how much will you win? So they want just the win amount, not the take-home amount. All I can say is be careful when you're reading them, okay? So then the situation, the first one, you get an ace. So you win $100. The chance of getting an ace is 1 out of 52. Ace of hearts, excuse me. If you get any of the other aces, well, there are 3 of them. That would be 3 out of 52. If you get a heart except for an ace, well, there are 13 hearts. 1 of them is an ace. So that's 12 out of 52. And all the other cards, well, we've used up all of these cards. Okay. So 52 minus that gives you 36 remaining. So again, you really have 2 distributions in this picture. This would be the take-home distribution. Those are your random variables. And this is the one amount random variables. Okay, it says find the expected value. Well, the expected value is this times this, plus this times this, plus this times this, plus this times this. Or you could put this in list 1 and this in list 2, and you would get, if you wanted to shorthand your work, I mean, there's not that many, I'd be okay with you doing like 100 times 1 over 52 plus 0 times 36 out of 52 and giving the answer, okay? But you have to show that you knew what you were doing. So then the question is, should we play this game? Costs you $5 to play, and on average, if you played over and over and over and over again, you're only going to win $365. So should you play? No. That's not saying that you win $365 once. It means the combination of wins and losses are going to come out to $3.65. Okay? All right. Now, lastly, we have to talk about standard deviation. Again, you can get it right out of the calculator. I feel like we should do one more of these problems. So we're talking about, this could be on your homework. Suppose the absent rate if you're on a day shift is 1%, and the absent rate if you're on a night shift at a job is 2%. Okay? What we're asking is the shift you work and the probability of being absent independent? Or are you more likely to be absent, it looks like, at night? Okay? When we say 60% of employees work the day shift. First off, let's look at the table. Well, 60% chance you work the day shift, 40% chance you work the night shift, right? Because they said 60% of employees work the day shift. Now let's look at it. Well then, if you work the day shift, there's a 1% chance you're absent, so a 99% chance you are not absent. And if you work the night shift, there's a 2% chance you're absent, and a 98% chance you're not absent. Anybody have a question on how to make one of these trees? Okay, so let's look and see. It wants to know if they are dependent. No. Okay, they would be independent if the probability of absent and working the day shift was the same as the probability of being absent and working the night shift, right? The probability of absent would be the same as the probability of absent no matter what shift you work. But that's not true, because if you work the day shift, you're only likely to be absent 1% of the time, but if you work the night shift, you're likely to be absent 2% of the time. So there's some dependency there. Okay? Now, here's the question. What's the probability of working the day shift given you were absent? So I know this employee didn't show up, and I'm trying to guess whether they're on the day shift or the night shift. Use the formula, absent and day shift over probability of absent. Okay? Well, probability of absent and day shift, that's day shift times absent, all over the probability of just absent. Well, you can be absent this top way, which will match this. No, they don't cancel out. Or you could be absent that way. So 42% chance. Similarly, if I said, what's the probability of not being absent, not being on the day shift, so being on the night shift, given you're not absent, you do the same thing. Okay, not on the day shift, so night shift and at work. All over, both ways you could be on the night shift, and all over all the ways you could be not absent. So again, the table's pretty easy to make, or not the table, the tree's easy to make. You just have to know how to use the formulas. Okay? And basically the formula is just getting rid of the denominators and counting up the pieces from the table. But I'll show you another example of that later. All right, last but not least then, if we were to make that into a table, okay? So I highly recommend you don't make a table unless they make you. But otherwise, we'd say, okay, how many people are on the day shift? Okay, well, if I let n equal 100, that, or 1,000, so we're looking at a 1,000-person company, then 600 are on the day shift. Okay, and I know that there are 1,000 people total, so that would be that 400 are on the night shift. Okay, and now it says the probability of absent given day shift is 1%. So I say, well, there are 600 people on the day shift. 1% of that would be 6. So then this would be 594. Similarly, I do the other thing. And now the question's really easy to ask. Probability of day shift given absent. Well, I knew 14 people were absent. What's the chance of them being on the day shift? 6 out of 14. Now, if we really wanted to look at it, oh, this won't work because there's some interdependence. That doesn't matter. Well, okay, let's look at it this way. Notice how the formula is the probability of day shift and answer absent all over the probability of absent. What's the probability of day shift and absent? Day shift and absent, 6 out of 1,000. Does that make sense? Divided by the probability of being absent, well, how many people are absent? 14 out of 1,000. When you divide fractions, that's the same as multiplying the reciprocals. That's why this formula works. It takes the probabilities and gets rid of the denominators. Okay, so that's that. That is the rest of the unit.